All right, welcome to this explainer. Today we're unpacking what is basically the ultimate masterclass, how to actually build an artificial mind right from the ground up. We're going to pull straight from the historic playbook of the DeepMinds team. So if you've ever wanted to trace the exact educational and technical path required to engineer true intelligence, you are absolutely in the right place. Let's get into it.
We really have to ask ourselves, how do we get from simple lines of computer code to an artificial general intelligence that can solve some of humanity's oldest, toughest scientific challenges? Because it's not just about typing away at a keyboard. It's a complete journey, one that requires us to totally rethink what intelligence actually is and then engineer it from first principles. Here's our roadmap for today. 1. The quest for AGI. 2. Inspiration from the brain. 3. Reinforcement meets deep learning. 4. Games as training grounds. 5. Solving real-world problems. And finally 6. The future of intelligence. Section 1. The quest for AGI. We've got to start by defining exactly what kind of intelligence AI engineers are actually trying to build here.
The ultimate goal is artificial general intelligence, or AGI, and what that really means is creating a flexible system that learns continuously, kind of like a human does. It's all about cognitive breadth. We aren't talking about a glorified calculator that just crunches numbers really fast. We are talking about a system that can face a completely novel problem, something it has literally never seen before, and just figure it out on its own.
To put that into perspective, the leap we're talking about is massive. Back in the 90s, you might remember the famous Deep Blue system beating Garry Kasparov at chess. But that was pre-programmed narrow intelligence. It could only play chess. Contrast that with AlphaZero. AlphaZero started with zero human knowledge, basically played against itself, and mastered chess by dinner time. That's the difference. True AGI learns dynamically from its own experience without any hard-coded human rules. Moving on to Section 2. Inspiration from the brain. To engineer this kind of dynamic learning, the curriculum doesn't actually start with code. It starts with biology. DeepMinds founder, Demis Hassabis, hit the nail on the head here. He noted that the human brain is the only existence proof we have, maybe in the entire universe, that general intelligence is even possible at all. Think about that. Before you can write the software for a mind, you have to study the only working prototype we have. This grounding in neuroscience is really what separates true AGI engineers from standard computer scientists. Section 3. Reinforcement meets deep learning. So how do we actually translate that biological inspiration into a functioning machine? This is where the technical path really comes into focus. The absolute game changer was combining reinforcement learning with deep learning into one seamless loop. It works like this. An agent simply observes its environment, like literally just looking at the pixels on a screen. Then it takes an action, and it tries to maximize its score using a method called Q-learning. It builds knowledge entirely from first principles, just by chasing a higher reward. Now, if that sounds a bit too technical, just picture a toddler, right? A childlike being explores a living room, maybe tears up a favorite book, or throws food just to see what happens. It acts, it sees the reward or the penalty from a parent, and it naturally learns the rules of its universe. This reward-based reinforcement learning is the core engine of artificial intuition.
Section 4. Games as training grounds. Because, you have to ask yourself, where exactly do you train a newborn artificial mind without it breaking things in the real physical world?
Well, it turns out simulated video games provided the absolute perfect playpens for escalating AI capabilities. In Pong, the agent barely figured out how to hit the ball. But by Breakout, it creatively discovered how to dig a tunnel behind the bricks to rack up points. Then, using the exact same algorithm, it mastered 50 Atari games from scratch. Eventually, it even tackled StarCraft, navigating continuous flows of missing information and complex long-term strategy, very much like early humans navigating unpredictable environments. And the sheer creativity this training unlocked? Staggering. When tackling the ancient, incredibly complex board game of Go, the system played what became known as Move 37. It was this completely original, almost magical move that experts later calculated had only a 1 in 10,000 probability of being played by a human. The machine hadn't just memorized human play, it had discovered a totally new way to think. This milestone was so profound, it reverberated way beyond the game board. It became a global Sputnik moment. It proved to the entire world that an artificial agent could outsmart human world champions using an entirely new, learned intuition.
The race to build AGI had officially shifted into high gear.
Section 5. Solving real-world problems. Because after conquering games, the ultimate test was taking this digital blueprint out of the simulated playpen and applying it to physical biology.
The team set their sights on the 50-year-old protein folding problem. Proteins are literally the machines of life. They build and control everything in our bodies. But figuring out how a one-dimensional string of amino acids folds into a functional three-dimensional structure is an impossibly complex puzzle. If solved, though, it could help cure diseases like Alzheimer's and malaria, or even help break down plastics in the environment.
Now, the transition wasn't easy. Unlike a video game where an AI can just play millions of rounds to generate unlimited data, real biology relies on incredibly small, painstakingly gathered laboratory datasets. The team endured some really humbling failures early on. Their predictions were practically useless. But they didn't give up. They overhauled their entire pipeline, they integrated real biological domain knowledge and physics into the system, and eventually they achieved unprecedented, physics-defying accuracy.
The jaw-dropping result of this exact same AI playbook was the open release of 200 million folded protein structures. They didn't just solve one protein. They essentially mapped every known protein sequence in existence, and they just gave it all away as a free gift to humanity. It is a tool that is currently completely reinventing biological science as we know it.
Finally, Section 6. The Future of Intelligence. As we look at the immense, world-altering success of tools like AlphaFold, we really have to look at what comes next on this rapidly accelerating timeline. We are hurtling toward a crossroads where AGI will soon arrive. And when it does, it's going to fundamentally divide human history into a before and an after. This technology brings the potential for limitless scientific discovery, things like curing diseases or solving climate change. But we can't ignore that it also brings unprecedented risks of military misuse, autonomous weaponry, and really profound societal displacement.
So, I want to leave you with this provocative thought. The engineers have shown us the blueprint. They are actively building this mind from scratch, and it is learning way faster than anyone anticipated. So as this incredible, world-altering intelligence wakes up, what institutions, what global coordination, and what shared human values must we urgently build today to protect our tomorrow? Think about that for a bit. Thanks for joining me, and I'll catch you in the next explainer.